Welcome to AI Paper Slop. Today we are jumping straight into a paper titled, You Don't Need Strong Assumptions. Visual Representation Learning via Temporal Differences.
Such a great title, by the way.
It really is. It's from researchers at UIUC and NYU, and that includes Jan LeCun. So, for the quick summary, if you're building vision systems right now, you know that self-supervised learning uses a lot of engineered tricks. Things like image masking, aggressive random cropping, color jittering.
Yeah, all those strong inductive biases we rely on.
Right, to force a model to learn useful features from unlabeled data. But this paper basically proves that as your data scales, those exact tricks become massive bottlenecks. So the authors introduce a paradigm called temporal difference in vision, or TDV.
And they just throw out all those spatial augmentations.
Exactly. They throw them out and rely on just a single, purely causal assumption, which is that the immediate past predicts the immediate future. By jointly training a frame encoder and a motion encoder on video, TDV predicts the next frame's latent representation using just the current frame and the raw pixel difference.
Which is such an elegant approach.
It is, and the result is staggering. It matches state-of-the-art models like Dino and iBot on dense spatial tasks entirely without relying on the crutch of artificial augmentations.
Yeah. And it forces us to confront, a very uncomfortable reality about modern machine learning. We have spent, the last decade carefully handcrafting these spatial priors.
Telling the model, hey, if I zoom in on this dog and turn the image black and white, it's still a dog.
Right, exactly. We engineered those rules because historically we just didn't have enough data or compute for the model to figure out object permanence on its own.
But if these tricks work so well, and they do, right? Dino is an incredible model that powers countless applications right now. Why are we trying to get rid of them? What is the actual harm in keeping these engineered priors if they help the model learn?
Well, it comes back to what Richard Sutton famously called the bitter lesson. The overarching history of AI is researchers slowly accepting that building our own human knowledge into systems works really well in the short term, but it inevitably loses to general methods that leverage massive scale in the long term.
Right.
The paper actually uses this brilliant biological analogy to frame this. So, think about insects. They have these heavily hard-coded survival behaviors in their genomes. They are born knowing exactly what to do.
So in machine learning terms, that's a very strong inductive bias.
Exactly. So insect-like AI models are rigid. They get up to speed incredibly fast because the rules are baked in, but they hit a ceiling because they just can't adapt beyond their programming.
Whereas mammals, and humans especially, we hard-code very little behavior into our DNA.
Yeah, we rely almost entirely on learning from experience over our lifetimes. We have much weaker inductive biases, but it gives us vastly greater asymptotic performance over time.
And we're basically making that exact evolutionary leap in visual representation learning right now. Early convolutional neural networks assumed spatial locality was everything. Then vision transformers dropped that local bias for global attention, and they scaled way better.
Right, and TDV is just the next step. It's dropping the engineered spatial rules and letting the temporal data speak for itself.
It makes sense conceptually, the training wheels eventually slow you down. But do we have hard proof that this happens in practice?
Yeah.
How do we know these biases are actively hurting a model at scale rather than just being, unnecessary?
We actually do. The paper quantifies that using image masking as a proxy for the strength of an assumption. The authors trained models on various subsets of the ImageNet dataset.
Okay.
If you train a model on just 0.1% of ImageNet, so extreme data scarcity, a heavy 30% masking ratio actually trails behind a 50% masking ratio by over 12 percentage points.
Well, meaning when data is scarce, the model desperately needs that stronger assumption, the 50% masking, to learn anything remotely useful.
Exactly. It needs you to force it to find the high-level semantics because it just doesn't have enough examples to learn them naturally.
That's the insect phase.
Right. But when you scale that exact same experiment up to 100% of the ImageNet dataset, the 30% masking actually surpasses the 50% masking.
So the optimal strength of your inductive bias objectively decreases as your data grows.
Yes, precisely.
For the engineers listening, think about this practically. Augmentations like color, jitter, and cropping, they really are training wheels. They absolutely keep your model from falling over into representation collapse when you have a small data set.
Yeah, they do.
But if a downstream task actually needs color information, say you are building a model to identify the ripeness of agricultural crops or, the specific material properties of a fabric, if you used aggressive color jitter during pre-training, You've actively destroyed that information.
You forced the model to become blind to something that might actually be critical. You are artificially capping the model's ceiling. The problem, however, is that if you just rip the training wheels off an existing architecture, the bike crashes. The authors demonstrate this brutally. They took the Dino architecture and progressively stripped away its biases.
And what happened?
By the time they removed the random cropping entirely, the top 1 accuracy dropped to less than 1%.
Less than 1%. Let's define what is actually happening there for a second. That 1% accuracy means the model is experiencing catastrophic representation collapse.
Complete collapse.
Because without the augmentations forcing the model to push different images apart in the latent space, it just takes the lazy route. It maps every single input image to the exact same constant vector and learns nothing. So if we strip away these spatial augmentations, what takes over? What provides the learning signal to prevent that collapse?
The replacement they propose is causality, the fundamental physical principle that causes precede their effects, and the immediate future is predictable from the past.
Okay, causality.
Yeah, because spatial augmentations are only ever approximately correct. Like a severely cropped image of a dog's leg might actually look mathematically identical to a table leg, which confuses the model. It's domain-specific and error-prone.
But causality is domain agnostic and exactly correct. The past strictly precedes the future.
Exactly.
Now, if you're listening to this and thinking, wait, if predicting the next frame is so powerful and causality is an exact signal, why hasn't computer vision just done this from the start? What was stopping us?
Well, we were bottlenecked by our datasets and our compute. For a decade, the gold standard has been static datasets like ImageNet.
Just millions of disconnected pictures.
Right. You cannot learn that the past causes the future from a single photograph. It lacks the temporal dimension entirely. So implementing this requires moving away from static datasets entirely and training on video sequences.
And for this paper, they used the something v2 dataset, right? Which is this massive collection of egocentric video clips showing humans interacting with objects, opening boxes, dropping pens.
Yeah, it provides the natural flow of time.
I do want to clarify the philosophy here, though, because when we throw the word causality around in ML, it can get a bit murky. We aren't talking about pure hard determinism here.
No, definitely not.
We aren't violating quantum mechanics and suggesting a neural network can perfectly predict the future state of every atom.
Right. We're just assuming the immediate macro-level future is predictable enough to force the network to learn useful representations. Like, if a hand is moving toward a cup in frame 1, it will probably be slightly closer to that cup in frame 2.
You don't need to predict the exact microscopic lighting changes. That macroscopic predictability is all the signal the model needs to start abstracting the visual world.
Exactly.
Let's translate this philosophy into the actual math, though. How does TDV encode this into an architecture without falling back into that lazy representation collapse?
It uses a remarkably elegant additive equation. It's z sub t plus delta z sub t equals z hat sub t plus 1.
Okay, let me work through that. So z sub t is our frame encoder. It looks at the current frame in the video, let's call the raw frame x sub t, and creates a compressed, abstract representation of it in the latent space.
Correct. Then we introduce the motion component. We take the raw RGB pixel difference between that current frame and the very next frame. And we'll call that sparse pixel difference delta x sub t.
Which is intrinsically lower rank than a full image, right? Because most of the scene, the walls, the lighting, the background, it doesn't change from 1 millisecond to the next.
Exactly. Only the moving objects contribute any non-zero signal. You feed that sparse pixel difference into a second network, the motion encoder. But here's the trick. The motion encoder doesn't process that pixel difference in isolation.
Okay, what does it do?
It conditions its processing on the current frame's latent representation, that z sub t, using cross-attention.
That is a crucial step, because the exact same cluster of shifting pixels means radically different things depending on the context. Like, a patch of brown pixels moving to the right could be a dog running, or it could be a dead leaf blowing across the street. The motion encoder needs the semantic context of the full frame to understand what the motion actually represents.
Yes. It needs to know what is moving to accurately encode how it is moving. So the motion encoder grounds the pixel difference in the frame's context and outputs delta z sub t.
Which is the predicted change in the latent representation space.
Exactly. Finally, you perform the additive composition. You add z sub t and delta z sub t together, giving you z hat sub t plus 1, which is your prediction for the next frame's latent state.
Wait, if I'm taking a base frame and then just encoding the motion vectors to predict the next state. This architecture is basically a latent space neural version of a classic H.264 video codec.
It is. It's performing the exact same conceptual separation. Classic video compression establishes an iframe, a base image, and only encodes the motion vectors for subsequent frames.
It forces the system to separate the static content of the scene from the dynamic motion.
Right, and TDV is doing that, but instead of predicting raw pixels, it's doing it in a high-dimensional semantic latent space.
But we still haven't solved the collapse problem, because if the frame encoder just decides to output the exact same constant representation for every single frame, then z sub t equals z sub t plus 1.
Yeah, the required motion becomes 0.
The loss drops to 0, and the model cheats its way to a perfect score while learning absolutely nothing. How does TDV escape this trap without augmentations?
Through a student-teacher framework, you maintain 2 separate copies of your frame encoder. The student network is updated normally via gradient descent, but the teacher network is an exponential moving average, or EMA, of the student.
For those who might be rusty on the terminology, an EMA teacher means its weights are just a heavily smoothed, delayed version of the student's weights.
Right. It updates very slowly. The student is predicting the next frame, but the target it is trying to hit is generated by that slow-moving teacher. To prevent the collapse, TDV uses a weighted combination of 2 distinct losses.
What's the first one?
First is the temporal prediction loss, just a standard mean-squared error. This enforces the causal physics constraint. It ensures that the current frame plus the motion actually equals the teacher's encoding of the next frame.
And the second loss?
The self-distillation loss, or LDNO. This is a cross-entropy loss applied to projection heads over both the global CLS token and the individual spatial patch tokens.
And that actively prevents the collapse.
Exactly. By forcing the student and teacher prototype distributions to match without collapsing into a single uniform distribution, it forces the encoder to maintain rich, discriminative representations.
So we have an architecture purposefully stripped of all those semantic augmentations. We aren't forcing the model to learn that a heavily color-jittered, zoomed-in dog is still a dog, which implies that testing this model on standard old-school ImageNet classification wouldn't really make much sense.
No, it wouldn't, and the authors are very upfront about this. If you strip out semantic priors during training, you won't get peak semantic performance on semantic benchmarks. To explain this, they actually introduce a concept from neuroscience: the brain's ventral stream versus the dorsal stream. In the human brain, the ventral stream is the what pathway. It's responsible for object identification. Like when you look at a coffee cup and think, that is a coffee cup, that's your ventral stream.
And standard machine learning benchmarks like ImageNet linear probing or K-nearest neighbors classification, those are essentially measuring ventral stream skills.
Exactly. And because TDV explicitly removes semantic priors, its ImageNet top 1 KNN accuracy, where it just looks at the closest feature matches in the latent space, is understandably low. It sits at just 8.79%.
Which makes sense. But what about the dorsal stream?
The dorsal stream is the where and the how pathway. It handles spatial awareness, motion, and coordinating physical actions. It's what allows your hand to naturally shape itself to the exact contours of that coffee cup as you reach for it, without conscious thought.
And this is exactly where TDV shines.
Yeah.
So what kind of dense spatial tasks we're talking about here? Let's put some concrete numbers to this dorsal stream performance.
We are looking at semantic segmentation on highly complex datasets like 8020K and cityscapes, and optical flow estimation on the MPI scintille dataset. These tasks require precise pixel-level understanding of space, geometry, and movement.
How did it do?
On these dorsal tasks, TDV matches or outright beats highly engineered models like Dino and iBot.
Wow. The PCA visualizations in the paper really drive this home. They take the raw patch-level features produced by TDV and map their principal components to RGB colors.
They're breathtaking to look at.
They really are. They are spatially coherent and tightly aligned with the actual physical boundaries of the objects in the video, often significantly better than Dino. The temporal difference objective just forces the model to deeply understand the physical structure of the scene.
So if you are building an app to classify dog breeds from a static photo, TDV isn't the tool for the job right now. But if you are building the perception stack for an autonomous drone navigating a forest, or a robotics pipeline picking items off a cluttered conveyor belt, or a 3D scene understanding model where spatial correspondence is king TD, gives you Dino-level performance without baking in artificial spatial biases.
That is a massive leap for embodied AI. But I want to pivot to honestly my favorite part of the paper. Getting a model to learn from the pure flow of time isn't as simple as plugging in equations and hitting compile.
Oh, definitely not.
The authors included an extensive section detailing all the things they tried that failed spectacularly. The graveyard of ideas.
Which is so rare to see.
And for an ML engineer listening to this deep dive, negative results are pure gold because they save you weeks of wasted compute. So let's dig into the failures.
The first major failure was incorporating IBBot-style grid masking. The idea was to mask out patches of the image to force the model to predict them, hoping to improve spatial performance even further.
And what happened?
The moment the masking ratio exceeded 10%, the model underwent immediate representation collapse.
Wow, why does masking work so well for IBOT, but completely destroy TDV?
It comes down to how the motion signal is computed. TDV relies on the raw RGB pixel difference between frames, that delta x sub t, to understand motion. If you apply a heavy spatial mask to the frame, you are literally deleting the local pixels required to track that small frame-to-frame movement.
So the motion encoder loses its input signal.
Exactly. The temporal link is severed and the model just collapses.
What about teacher sharpening? Dino is famous for its asymmetric temperature trick, where the teacher network gets a lower softmax temperature to artificially sharpen its predictions. It's kind of a staple of self-distillation. Did that work here?
It consistently performed worse. TDV absolutely needed identical temperatures for both the student and the teacher to remain stable.
That seems counterintuitive. Why would an asymmetric temperature be necessary for Dino, but actively harm TDV?
You have to look at the underlying mechanics of what the loss function is doing. Dino forces two artificially distorted, augmented views of the same static image to agree with each other. So it needs a sharper teacher target to cut through the noise of those heavy augmentations and force the network to find the shared semantics. TDV, however, isn't dealing with distorted views.
Right. It is supervising an actual, feasible next frame prediction in time. It's trying to predict literal physics, not force mathematical agreement between two crops.
Exactly. A sharpened teacher distribution in TDV artificially and incorrectly narrows the acceptable motion predictions. It assumes absolute certainty about the future state, which destabilizes the learning signal because the physical world has natural variance.
That makes a lot of sense. They also mentioned that resetting the EMA teacher failed. Sometimes in SSL, engineers will reset the EMA if they worry the teacher network is getting stale or stuck in a rut.
Yeah, but doing that here introduced massive instability.
Because TDV relies entirely on the smooth, continuous evolution of the teacher to map the continuous evolution of time in the video.
Right, an abrupt reset shatters that temporal consistency. The student suddenly has to predict a wildly different latent space for the next frame, breaking the causal chain entirely.
So out of the standard bag of SSL tricks, what actually survived the transition to temporal learning?
Well, positional encodings were a fascinating result. Standard absolute positional encodings consistently outperformed more modern relative encodings like ROPE.
ROPE, or rotary position embedding, is incredibly popular in language models right now because it calculates the relative distance between tokens. Why wouldn't a relative encoding work better for tracking motion, which is inherently relative?
Because while the motion is relative, the objects moving exist in an absolute physical space. To predict how an object is going to move across a frame, the motion encoder needs a fixed, absolute coordinate system to anchor its predictions.
Relative encodings just float too much.
Exactly. Furthermore, applying the Dino cross-entropy loss to the global CLS token and including that CLS token in the cross-attention block was highly critical.
That makes perfect sense mechanically, honestly. It grounds the motion encoder. It gives the network a high-level global semantic summary of the entire scene to anchor its pixel-level predictions. The motion encoder needs to know the context of the whole room before it can accurately predict how a single shadow is going to move across the floor.
It ties the local dynamics to the global context. Without it, the motion encoder just gets lost in the noise of individual pixel shifts.
We are looking at a massive shift in how we approach representation learning here. We are finally moving away from telling a model, hey, memorize these human-engineered rules about spatial invariance, and moving toward a paradigm of simply saying, observe how the physical world works over time.
And TDV proves that causality alone is a rich enough signal to build robust, structurally aware spatial representations.
It really does.
The implications for scaling are profound, really. Engineered biases inherently limit how much a model can learn from massive data sets. By removing them, the ceiling for vision model performance might be vastly higher than we currently estimate.
I want to leave you all with a final thought to chew on. Think about autoregressive large language models like GPT-4 or Llama. They scale to superhuman, astonishing levels precisely because they rely on a pure, domain-agnostic causal assumption.
Predict the next token.
Predict the next token. They don't use hard-coded semantic rules or human-engineered grammar trees, just the raw causal flow of text over time. Now that TDV proves we can use that exact same causal principle to predict the next frame's latent state in vision, completely without human-engineered image augmentations, are we looking at the fundamental blueprint for a true vision LLM?
It's the logical next step.
Right. Could this temporal difference mechanism be the key to infinitely scalable physical world models that learn everything they need to know simply by watching millions of hours of raw, unannotated video? It's a question worth asking the next time you find yourself manually tweaking the color jitter settings on a data augmentation pipeline.